Good afternoon, everyone. So let's get started. I see that people are still coming in. So I have a few questions for you guys today. Let's share our little trusty wheel here and see. I'll ask. So I'm going to do the first question. Let's see. Ryan Smith. Yay, Ryan is on. Okay. Nice, easy question. Ryan, how many tests have we looked at so far for a series? How many series tests have we looked at? Ryan, are you there? Okay. Ryan may be logged in, but have walked away. Okay, Dominique. Yep, she's on. Excellent.
Is it 5?
I think we've looked at a little bit more than that.
Uh,
Can you name the tests?
Um,
Give me two. Give me two tests.
is the P series test
Okay.
and the integral test?
All right. Good. Okay, let's see. All right, Skylar. Skylar, are you on?
Yeah, man.
Okay, can you give me the name of two more tests?
Um, the geometric test
Okay,
and
geometric
the
series. And what else?
and the nth term.
Okay, nth term test of divergence. All right, very good. Let's see. All right, Kyle. Kyle, are you on?
Yes.
Good. Can you give me the name of some other tests?
Uh, all right, I'll be honest. I was making a sandwich, so I wasn't entirely listening to the ones that were already said.
Okay. All right. Well, you know what? I so appreciate your honesty. Okay, let me spin again. I think that's Destiny. Okay, Destiny, are you on?
Yes, I am.
Okay. Any other tests that we've looked at?
Um, did someone? I don't think anybody said telescoping, right?
Nobody said telescoping. Excellent.
Um, I think that's all I have.
Okay. For some reason, I feel like there were more tests that we looked at. Oh, yes, they definitely are. Okay, definitely are. So some tests that we did on yesterday. So spin again. And okay, got Ryan again. Ryan, are you on? Okay, Ryan's still.
I'm
Ryan,
here.
you are there. Okay, good. We called you the first time, but I missed you. So what other tests are on? What did we do?
I just heard telescoping.
Okay, so far we've had the geometric series test, the telescoping test. We've had the nth test of divergence. We've had the integral test, and we've had the P series test.
The comparison tests.
All right, and how many are there? Comparison tests.
There's two.
Okay, and what's the difference between the comparison tests?
The difference between them.
Yes.
Isn't one comparing the limit?
Okay, good. One is looking at the limit and the other one is
A direct comparison?
direct comparison tests. Okay, I have another question. Nigel. Nigel, are you on?
Yes, I'm here.
Okay, excellent. Which tests actually give you the sum of the series? There's some of them that can only tell you whether it converges or diverges, but there's a couple of tests that can actually tell you the sum of the series. Which tests actually give you the sum?
Uh, I'm not too sure.
You're not too sure? Okay, so there were some series that I said you can actually use this formula and it will give you a number, and that number is the sum of the series. Does that help any? Okay, if not, that's okay. Let's see if we can get a classmate to help you.
Is it geometric?
Okay, good. Geometric series is 1.
And then nth term test, does that do it too? Or
Well, the nth term test is not going to give you the sum of the series. There's one other test that actually tells you what the sum of the series is. And it was on the exam. Okay, I see somebody in the chat. All right, Lauren, that's right. It was the telescoping series. Okay, I have one more question. I think Destiny, did I get you before? Destiny, have you answered a question?
Yes.
Okay, I won't pick on you again. We'll let the wheel pick somebody else. All right, Benny Lee. What is the difference between a sequence and a series?
I know a sequence is a list of numbers,
Okay,
and a series is, oh man, it's not coming to me on the series, but I know the sequence though.
okay, I'm
Nobody
proud
knows
of you.
because I just can't think of it right now.
Okay, anybody want to help Benny?
You said the difference between a sequence and series?
Yes.
A sequence is like it's like a list that has a pattern, but
Okay,
a series is like a bunch of different numbers or fractions being added together
okay.
that also follow a pattern.
All right, so that's exactly right. So the sequence is a list of numbers that can be described by some kind of formula or pattern. So it's just a list. And the series is the sum of those terms. Okay, good way to start off the class. I think hopefully everybody's kind of got a good idea of what we're doing. So we're going to now go into another test. This test is called the alternating series test. And we've seen several alternating series. So let's see, I think we are up to number 8. Let's make sure. The limit comparison test was number 7. Good, so we are up to number 8. And so number 8 is our alternating series test. And so with the alternating series, there's several things that we want to look at. Okay, so first, what does an alternating series looks like? Well, there was one on the exam. So here's an example of the alternating series. So an alternating series is, well, we had an alternating sequence on the test. Let's look at an alternating series. So let's say we're going to take the sum n equals 1 to infinity of -1 to the n minus 1 of n plus 1 over n. So now I want to look at this series. Okay, so the first term in the series turns out to be, we put in 1, so we're going to get 2 over 1. That's the first term, and it is positive. The second term is negative. So this is 3 over 2. The next term is positive. It is 4 over 3. And the next term is negative. It's 5 over 4. And we keep doing this, and we keep adding these up. And what makes this an alternating series is that the terms alternate from positive, which is not there, to negative, to positive, to negative, etc. So alternating series always have this -1 to the n minus 1, because that changes the signs of each term that is being added on. Okay, so this is why we have what we're going to have for our alternating series. So the series summation n equals 1 to infinity of -1 to the n, and then I'm going to call this un. So un is some term. So this is going to look like u1 minus u2 plus u3 minus u4. So as you can see, the u's are just individual terms of a sequence, but we alternate the signs when we're adding them together to create the series. All right, so this sequence converges if 3 things are satisfied. So the first thing is that all the UNs have to be positive. Second, it has to be a decreasing series. So that says UN has to be bigger than or equal to UN plus 1. All right, and this is for all n bigger than some number n, as we said. That means we can go out further enough in a sequence that eventually it just decreases thereafter. And 3, the limit as n approaches infinity of un, whoops, has to equal 0. Okay, so this is an alternating series test. So we can look at several different examples, and we can use this to determine whether or not a series is going to be convergent. And now Series is asking me questions because she hears me talking to her. I got to turn her off. Okay, so let's look at the first example. the summation n equals 1 to infinity of -1 to the n minus 1 times 1 over n. Okay? All right, so as I look at this and I go back to see what I had before, that clearly says to me that my un is the 1 over n term. Okay, so un is the 1 over n. All right, so let's check our criteria. So 1 over n, where I un, which equals 1 over n, is positive for all n. So that's our first condition. Our second condition, we need to see, is it true that un is bigger than un plus 1? In other words, is this a decreasing sequence? So are the numbers 1 over n decreasing? So there's several different ways you can show that. So you can show that 1 over n is bigger than 1 over n plus 1. Okay, the easiest way to show that is multiply both sides and get n plus 1 is bigger than n, and this is always true. So that's one way you can show it. Another way is I can let f of x, well, f of n be defined by an. So I can take an and create a function of it. So if I do that, f of x would be the function 1 over x. So now I can take the derivative of it and get f prime of x is minus 1 over x squared, or negative 1 over x squared. And this is always negative for all x. Remember, x is not equal to 0. I need x bigger than 1. So therefore, that is always true. So both things show either way. Oh, I forgot. I need to go further. So both of these both show. Doesn't matter which way you decide to do it. So yes, it's true. un is bigger than un plus 1. And then the last piece is the limit as n approaches infinity of 1 over n, and that is 0, and that is one of the 7 special limits that I gave you. Okay, so this is also true. So by the alternating series test, the sum n equals 1 to infinity minus 1 to the n minus 1 times 1 over n is convergent. So this converges. Okay, any questions? Okay. Second example. Let's look at the sum n equals 1 to infinity of minus 1 to the n minus 1, 10n divided by n squared plus 6. Okay. So here un is 10n divided by n squared plus 6. All right, so I can see that UN, so my first condition, UN equal to 10n divided by n squared plus 6 is greater than 0 for all n, greater than 1, because any number I put in, if n is positive, 10n is positive, n squared plus 6 is positive, so therefore UN is positive. Okay. Number 2, is it true that UN is bigger than UN plus 1 for some n bigger than some number n? So we need to see if this is true. Okay, so now this one is a tough one in terms of just being able to look at UN plus 1. So for this one, I'm actually going to do the derivative again. So I'm going to say that AN is equal to F of n, where F of x, the function I want to look at, is 10x over x squared plus 6. So now let's look at its derivative. So that's going to be the bottom, x squared plus 6, times the derivative of the top, which is 10, minus the top, which is 10x, times the derivative of the bottom, which is 2x, all over the bottom squared. Which is x squared plus 6 quantity squared. So this turns out to be 10. I'm going to get 16 minus x squared. Is it 16 minus x squared? Let me see. Why did I get 16 minus x squared before? Maybe that's not correct. Let's figure it out. I can factor the 10 out of each piece. And when I factor the 10 out of each piece, the first piece is going to give me x squared plus 6. And then the second piece is going to give me minus 2x squared. Okay, yep, I thought I made a mistake in my notes. Okay, that's fine. At least I found it. So this is x squared plus 6 quantity squared. So therefore I get f prime at x turns out to be 6 minus x squared. Oh, it's still multiplied by 10. Can't throw away my 10. And then I want to divide by, whoops. X squared plus 6 quantity squared. Okay, so my question to you is when is f prime of x less than 0? Well, that's when x squared is bigger than 6. Okay, so that's for some x equal to 3. Okay, so therefore, after x equals 3, the derivative is decreasing. So if n is equal to 3, then un equal to 10n divided by n squared plus 6 is, that's going to be bigger than un plus 1 if the little n is bigger than 3. So at that point, it's decreasing. So therefore, yes, un is bigger than un plus 1 for n bigger than 3. Okay, so now the last part, it's part 3. So now we need to look at the limit as n approaches infinity of 10n over n squared plus 6. This time I think I'm going to use L'Hopital's rule. I don't use that much, but it works. So that's the limit as n approaches infinity. Take the derivative, I'm going to get 10. And in the denominator, I'm going to get 2n. And that limit is 0. So all three things by the alternating series test. Summation n equals 1 to infinity of -1 to the n minus 1 times 10n divided by n squared plus 6 converges. So that is the alternating series test. Okay, let's look at another example, number 3. So this is the sum n equals 1 to infinity of -1 to the n of n plus 1 over n. Okay, so this one is the first one I had mentioned. All right, so the question is to find out whether or not this series is convergent or divergent. I may as well put my -1 there. So we're going to use the alternating series test. So when I go to use the alternating series test, I look at my first criteria, and that is un equal to n plus 1 over n is positive, okay, for all n. N's positive and n plus 1 is positive, so n plus 1 over n is positive. Now, I'm looking at this one and I'm thinking to myself, if un, which I didn't write, is n plus 1 over n, I can look at that right away and say that the limit of un is 1. So I'm going to skip down to number 3 and not even bother with number 2 for a minute and say that the limit as n approaches infinity of n plus 1 over n, again, I'll use L'Hopital's rule. So this is the limit as n approaches infinity of 1 over 1 is 1. And that thing is not 0. So the only thing I can say about this is the alternating series test is inconclusive. It does not say that this series diverges. It just says I can't use the alternating series test to determine it. Okay? All right. Any questions about these? Any questions? Okay, so I'm going to give you 3 problems to solve. And that should say determine using alternating series test if these series converge or diverge. So the first one is the sum n equals 1 to infinity of minus 1 to the n minus 1 times 1 over the square root of n. That's number one. Number two, the sum n equals 1 to infinity of minus 1 to the n times 1 over n 3 to the n. And then number three, the sum n equals 1 to infinity of minus 1 to the n minus 1. I'll give you, trying to think, I want to give you a toughie. 1 over the square root of n plus the square root of n plus 1. Okay. Any questions about those three problems? Okay. Okay, so we're all back from the breakout rooms. All right, what you think, guys? Tell me what you think about those problems. How far did you get? Where did your group come up with? Hello, can y'all hear me? Okay,
Hello?
Miles.
My group came up with that all of them converged.
Okay. All right, that all of them converged. Anybody else?
Yeah, I was ready to agree with Lauren. We got through the first two and found out they converged.
Okay, so you were able to use the different parts of the test to show that they converged. Anybody whose group had some trouble? Okay. All right, so that is the alternating series test. So now I want to talk to you about absolute convergence. All right, so with absolute convergence, this is another test. All right, I tend to make it a test so that you can get an idea of all of these different parts of this. So the last thing we did was the alternating series test, and that was number 8, I believe. Good, so now we are looking at number 9. So this is the test of absolute convergence. All right, so the test for absolute convergence is a series The summation n equal 1 to infinity of an converges absolutely. If the corresponding series of absolute values converges. So in other words, if the summation n equal 1 to infinity of the absolute value of an converges, then the summation n equals 1 to infinity of an converges absolutely. So let's say, for example, let's look at the summation n equals 1 to infinity of minus 1 to the n over n squared. So that right there, I could use on this test, I could use the alternating series test, but I can just look at this and say, let's check out the summation n equals 1 to infinity of 1 over n squared, because that is an absolute value. So that's the absolute value of that series. Now, does this series converge or diverge? What kind of series is it? And does it converge or diverge?
I don't remember what series it is, but it converges.
Okay, why does it converge?
Because I don't remember.
You're
I just
so
have it in my
close.
notes. I said it converges because, let me scroll. It says that for is it because it's bigger, or that the n is larger?
No, not quite. This is a particular kind of series.
Maybe, okay, if I'm saying it's a P series, then it converges.
Yes, good. This is a P
greater than 1.
series. This is a P series where P is equal to 2, which is greater than 1. Okay, so this series converges. So therefore, the summation n equals 1 to infinity of minus 1 to the n over n squared is going to converge absolutely. Now there's a theorem that says if a series converges absolutely, then it converges. So therefore, this series converges. Okay. Number 2, summation n equal 1 to infinity of the cosine of n over n to the 3/2 power. Okay. All right, so here I need to look at the absolute value. So let's check out summation n equals 1 to infinity of the absolute value of the cosine of n divided by n to the 3/2 power. Now, how can I determine if that series converges? How can I determine if this series converges? I'll give you a hint. The absolute value of the cosine of n is less than or equal to 1. Does that help?
We do like a comparison test with the geometric series.
Say that again.
Do we do a comparison test with the geometric series?
Okay, we can do a comparison test. That is excellent. But it's not the geometric series. It's the P series again. Okay, thank you, Ian. That was really good because some people cannot see that. All right, so that cosine of absolute value cosine of n less than 1 does help. So here's an is equal to the absolute value of the cosine of n over n cubed. And here's bn equaling 1 over n, I'm sorry, not n cubed, n to the 3/2 power. Okay, so now we can say that an is less than or equal to bn for all n. Okay, and the summation n equals 1 to infinity of 1 over n to the 3/2 converges by P series, P equal to 3/2, which is greater than 1. So now, by the direct comparison test, Ian says that I can say that the summation n equals 1 to infinity of the absolute value of the cosine of n over n to the 3/2 converges. Okay, so we have the direct comparison test is here. an is less than bn, and this series converges. So therefore, this series converges. But this series converges implies that the summation n equals 1 to infinity of the cosine of n all over n to the 3/2 converges absolutely. So the test that I used here, we used the P-series test. Then we used the direct comparison test. And then we used the test for absolute convergence. So on the exam or any other quiz or whatever, you're going to need to be able to say, these are the tests that I use to make the conclusion that the series I started with converges. I used the P-series to show that the first thing, then I used a comparison test with that convergence series, and then I used the absolute value, the test of absolute convergence. Okay, any questions about that?
I had a question about the hint that you gave us with the
Yes,
absolute value of cosine being less than or equal to 1. So
yes.
that hint, did it tell us to use P-series or?
No, that hint tells you to use the comparison test.
Oh, okay, got it.
Okay, the hint that it's less than or equal to something means I'm directly comparing them. So that gives me the idea that I can use maybe the direct comparison test. So then when I go down to the line that says AN and BN, then that gives me the direct comparison test. I don't use the P-series until I have to show that 1 over n to the 3/2 converges. Okay.
Thank you.
You're welcome. Any other questions? Okay, we have just a few more minutes. I'm going to do another example of this and then one more test. Summation n equals 1 to infinity of -1 to the n times 1 over n. Now we've already shown using the alternating series test that this series converges. The question is, does it converge absolutely? Okay. All right. Well, we need to look at the summation n equal 1 to infinity of its absolute value, which is just 1 over n. Now, what do we know about this series? It has a name. What's its name? This series has a name. What is it?
Harmonic series.
Good. So this is the harmonic series. And is it convergent?
No.
No. It is not convergent. It diverges. Okay, so since the sum n equals 1 to infinity of 1 over n, which is the sum n equals 1 to infinity of the absolute value of the original sequence series that I gave you, diverges, then this sequence n equals 1 to infinity of minus 1 to the n over n does not converge absolutely. Okay, so that leads us to the last test of today, and that would be number 10. Yes, number 10. This is the test for conditional convergence. Okay. All right. So here's a definition. A series that is convergent but is not absolutely convergent is called conditionally convergent. Okay. Okay, so that last example that we gave, so let's just recall for a minute. The sum n equals 1 to infinity of minus 1 to the n over n. So we showed by the alternating series test that this series is convergent. Then we showed by the test for absolute convergence that this series is not absolutely convergent. Hence, it is conditionally convergent. Okay, so this is what you need to do. Whenever you're looking at an alternating series, so you're given an alternating series. Okay. The first thing you're going to do is check to see if it's convergent or divergent. So here is my series. Okay, so I'm going to use the alternating series test. All right, so I'm going to use the alternating series test. And I find out that it's convergent. Then I need to go on oh my goodness, why can't I get an arrow? I think it's time for me to replace the pointer, my pointer. Then I need to use the test for absolute convergence. Okay, and I need to do the alternating, I need to do the test for conditional convergence. So here, when I do the test for absolute convergence, if the summation n equals 1 to infinity of just un converges, then it's absolutely convergent. And here, if the summation of n equals 1 to infinity of un diverges, then it's conditionally convergent. And then, of course, the alternating series test, the other possibility down here is it can be inconclusive. And then you just got to use another, then you have to figure something out. Okay. So whenever you use the alternating series test, after it, you need to then see if it's absolutely convergent or conditionally convergent. Okay. Any questions? Any questions? Any questions? Okay, so on tomorrow, I will let Mr. Williams go over those 3 problems that we did in the breakout room during recitation, so he can help you there. And then on Thursday, we will be covering our last 2 tests. And then we will sum up everything in terms of all of the series tests that we have used and a good way of trying to remember them. Okay, any questions? Okay, I'll see you guys either tomorrow in office hours. Email me if you want to come to office hours, or I will see you Thursday. Have a great day.
Have a good day.
Have a good one.
Bye.